Hi everyone. I only got one feedback question today, but I thought it was a pretty good overall encompassing feedback question, so I definitely wanted to make a video responding to it. How did you determine that ammonia, NH3, had dipole-dipole forces? What are the rules or characteristics of each type of force? How do we identify them from looking at the structure? For example, the example with CO2 and NO2 was confusing. How do I determine which forces are found and how strong each force is? So generally, if you're dealing with molecular compounds, there's really only two types of forces that you're going to need to concern yourself with. Dipole-dipole interactions and London dispersion forces. And basically, if you want to know how do you identify which forces a molecule experiences, every compound, every molecule experiences London dispersion forces, no matter what. They are the result of random fluctuations in electron density, and every molecule has electrons, so you can have fluctuations in them. And those fluctuations create temporary dipoles, and those result in net attractions between molecules. So every molecule has London dispersion forces. Only molecules which are polar that have net dipoles will experience dipole-dipole forces. And generally speaking, dipole-dipole forces are stronger than London dispersion forces for molecules of comparable size. So let me say that again. They are generally, dipole-dipole forces are stronger because the charges are long-lived. They are permanent dipoles. London dispersion forces are only temporary dipoles, so they are not long-lived, they're not very strong and stable, and so generally dipole-dipole forces are stronger unless you have a very, very large molecule. And very large molecules have a lot more electrons, and so their fluctuations in electron density are, what's the word I'm looking for? Can be more severe, for lack of a word. They can be more important. So I normally won't try to give you questions of that kind where it's not clear, okay, how do you, let me put it this way, it's not easy to make a distinction between which is going to be stronger, dipole-dipole or London dispersion forces for a lot of cases. If the molecules are a comparable size and comparable molecular weights, if one molecule has a dipole, then that one is probably going to have stronger intermolecular forces because the London dispersion forces are much, much weaker and they are of negligible importance. Now, how do you know when something is going to experience dipole-dipole interactions if it has a net dipole? So, for example, ammonia, NH3, has a net dipole. We talked about on Wednesday that molecules which have net dipoles are those that have polar bonds. So these are polar bonds. Nitrogen is more, I actually just realized I have these backwards. Nitrogen is more electronegative than hydrogen. So these bonds actually should point, these dipoles should actually point the other way, towards, towards the nitrogen. And so because of this molecule, so that's the first criteria. The second criteria is the molecule should be asymmetric in some fashion. So this molecule is not symmetric. It has this general shape. It's trigonal pyramidal. So the electrons are being pulled towards the top of the molecule, and so the top of the molecule has higher electron density. That gives it a net dipole. So how do you determine whether something's going to have dipole-dipole forces is whether it has a net dipole. So I spent all of Wednesday's lecture explaining when something was going to have a net dipole that was going to be a polar molecule. How can you compare the relative strengths of dipole-dipole interactions? It depends upon the strength of the dipole. The dipole is larger if the two molecules have a much larger difference in electronegativity. So let me give you an example of that. I'm going to do a quick little sketch here of boiling point versus period for the hydrogen halide, hydrogen halide molecules. So for instance, HF has a relatively high boiling point. HCl has a comparatively low boiling point. Now, why is that? It's because fluorine is significantly more electronegative than chlorine. If you look at these molecules, so you have HF and you have HCl. They both should have dipoles. They are both asymmetric. One of the atoms in the molecule is more electronegative, so it pulls electrons towards it. But fluorine is more electronegative than chlorine is. And so while chlorine does pull electrons towards itself, it doesn't do so as strongly as fluorine does in hydrogen fluoride. So they both experience dipole, they both have dipoles, and they both experience dipole-dipole interactions. But hydrogen fluoride's dipole-dipole interactions are much stronger because the size of the dipole is larger. Fluorine's pulling the electrons, the charge distribution is significantly more skewed for fluorine versus in HCl. And as a result, because you have stronger intermolecular forces, stronger dipole-dipole interactions, fluorine has a higher boiling point. A few other things. I'm sorry, I wanted to address your other question. How do you know that CO2 is not going to have dipole-dipole interactions? That's because CO2 is a linear molecule. It has bond dipoles. Oxygen's more electronegative than carbon, and the electrons are pulled towards the oxygen, but they're pulled in a symmetric fashion. Electrons are pulled just as much to the left as they are to the right, so you end up with a symmetric charge distribution, and you don't end up with a net dipole. NO2, on the other hand, does not have a linear geometry. It has a bent geometry because it has an extra electron. Well, I would have said a lone pair. It has an extra electron around the central nitrogen. So as a result, yet again, you do have dipoles. Oxygen is more electronegative than nitrogen. So the electrons are pulled towards this oxygen and they are pulled towards this oxygen, but they are not being pulled in opposite directions. They don't cancel each other out. And so you do end up with a very, very slight net dipole pointing towards the oxygens. And that is solely a fact of the geometry of NO2. CO2 is linear, and the dipoles point in opposite directions symmetrically. NO2, those dipoles do not point symmetrically or anti-symmetrically. They don't cancel each other out. So this one does have a dipole, and so it will experience dipole-dipole forces. They both experience London dispersion forces. Every molecule experiences London dispersion forces, but in this case, because they are comparable in size, I wouldn't say that one has significantly stronger London dispersion forces. Nitrogen technically does have an extra electron, so it should have ever so slightly stronger London dispersion forces. But much more important is the fact that it has a dipole, and that dipole, that permanent dipole, is more important in terms of the overall strength of its intermolecular forces. Now, I did say it can be tricky to note when our London dispersion forces, they increase with a number of electrons. So I had one last example of that today during lecture. Fats, oils don't have dipoles. They are mostly nonpolar molecules, but they generally have higher boiling points than something like water, H2O, because their London dispersion forces, while individually they are weak, there are significantly more molecules, significantly more electrons. And so you have significantly more opportunities for tiny fluctuations. And that is enough to outweigh the very, very strong interactions of dipole-dipole interactions for water. So it's not always going to be a clear-cut thing. If I continue with my original or my previous example here, hydrogen fluoride versus HCl, we said, okay, HCl, they both have dipole-dipole interactions. HCl has a weaker dipole, so it has a lower boiling point. If you look at HBr, HBr's boiling point is pretty darn close to HCl. Let me actually make this. HBr is just a little bit higher boiling point than HCl. And that might be confusing because HBr also is a polar molecule. Bromine is more electronegative than hydrogen, and so the electrons are pulled towards the bromine. But bromine's even less electronegative than chlorine. So its dipole should be significantly smaller. So if it has a smaller dipole, you would expect it to have weaker intermolecular forces, and you would expect its boiling point to be lower. But in fact, it's actually just a little bit higher than hydrogen HCl, than hydrogen chloride. So that seems to go against our basic understanding of dipole-dipole interactions. The explanation for why HBr is a little bit higher, well, if we continue with this trend, if you look at HI, hydrogen iodide, its boiling point is a little bit higher than HBr. So you still have the same trend occurring here that you expect, well, HI has an even weaker dipole than HBr. So I don't know if I can make this much smaller, but I'll try. It has an even smaller dipole than HBr. So you expect, again, smaller dipole should be weaker intermolecular forces, but that's the reason why we are confused here is because we're only thinking about dipole-dipole interactions, and we are forgetting that all of these still have London dispersion forces. HI has London dispersion forces, HBr has London dispersion forces, everything has London dispersion forces, and the strength of those LDF forces increases with the number of electrons. Fluorine, chlorine, bromine, iodine, those elements are going down the periodic table. And so you're getting elements with more and more electrons. So this is the same trend that we saw, I presented today, that Cl2, Br2, I didn't present I2, but I2 as well, their boiling points increase because they have more electrons, they have stronger London dispersion forces. So the point being that, okay, you get kind of like a weird shape here in terms of if you follow their boiling points. HF has the highest boiling point because, well, two reasons. One is, okay, it has the weakest London dispersion forces, but it has an incredibly strong dipole. And that very, very strong dipole is the most important factor for determining its relative intermolecular forces. It also experiences hydrogen bonding. So that, again, gives it even stronger intermolecular forces. HCl has a weaker dipole, and so it has a lower boiling point. It technically has stronger London dispersion forces, but they are not so much stronger than HF's dipole interactions that it should end up with a higher boiling point. It ends up with a lower boiling point because it has lower dipoles. And then as you continue on, yeah, you expect the dipoles to get weaker, and they do, but their London dispersion forces increase. And in this case, it turns out that London dispersion forces will win out over weaker dipoles. So short answer is it's not always going to be clear-cut. In some cases, it will be somewhat subtle. It won't be easy to predict the relative boiling points. I want people to be aware of that there is subtlety and that it can be complicated. And on some cases, yeah, you will have to make judgments on a case-by-case basis. That being said, I will reassure people that I don't plan on assessing on those subtle cases because, yeah, it's not immediately obvious. And I don't expect people to have the instinct yet. And I don't even have the instinct every single time. I can look at the data and I can explain why because I understand where the subtlety comes from. But I don't necessarily expect people to get that just yet. So generally, to go back here, how do you determine the relative strengths of intermolecular forces? You can make judgments about you can compare dipole and dipole interactions between two molecules that both experience dipole-dipole. So you can make that example with HF and, can I do this? And HCl. HCl having a weaker dipole than HF. Nah, whatever, I'm not going to try to do that. Having a weaker dipole means that it should have weaker dipole-dipole interaction, so it has a lower boiling point. But beyond that, as you go down into the lower halogens, their dipoles become less important, and more important becomes their London dispersion forces. And so you basically have two things to consider. And sometimes it will be clear-cut, and sometimes it won't. But I will try to give you examples where it's clear-cut. So for example, I give one example today between ammonia, NH3, and methane, CH4. And in that case, it's clear-cut that NH3 has stronger intermolecular forces because it has a dipole. CH4 only has London dispersion forces. It's symmetric. It has tetrahedral symmetry, so it doesn't have a dipole. And it's comparable in size. It's comparable in terms of its molecular weight and the number of electrons to NH3. So you can say that, okay, they're comparable in size, number of electrons, their London dispersion forces should be comparable. So then the only thing else I have to compare are their relative dipoles. And NH3 has a higher dipole. So then I would say NH3 has a higher intermolecular forces and a higher boiling point. So I hope that sort of summarizes and clarifies a few points raised during today's lecture. That's all I have for you guys, folks. Otherwise, I will hope everybody has a good weekend, and I'll see you on Monday.